Good morning, everyone. I hope everybody's doing well today. We don't have much more. I wanted to just take an opportunity today to sum up some things. We will not have class on Wednesday. There's really nothing more to say. You will have your final exam in the same testing window on Thursday and Friday. We've completed all the course material, and I appreciate your attention to the um, signature assignment. Also, our homework, the last couple of sections will be due on Wednesday at 11 p.m. And most all of you have been very good about completing your work. We're done with the extensions, okay? I've had to tell my pre-calculus classes the same, since they don't tend to have the best routine of getting things accomplished. So I appreciate the fact that you all have been very attentive to that. So the last due date will be enforced. And then, of course, your homework will be derived from the average of all, your homework grade will be derived from all the average of the sections that you've done. So again, I appreciate your attention to that. Also, the final exam is set up. I'm going to do some examples from the actual practice exam that you have on your website with the practice test. The final exam will contain approximately 20 questions, and there'll be a fairly standard coverage of all the material. There probably will be maybe maybe a couple of more questions on the newest material, but the coverage is fairly comprehensive throughout the course. So you can expect maybe 5 or so problems on the new material, which basically cover the topics that I have lectured on. So there, I've told many of you before that the final exam is probably the easiest test that you take throughout the term. Again, once you complete your homework, that will be done on Wednesday. And then, of course, when you take your final exam, the same protocols will be in place. Execute your Blackboard exam, and then scan your work, submit it with Turnitin on Blackboard, and then you are done. I'm giving you extra time, even though it is a little bit difficult to kind of cram everything in by giving you extra time, but I've always done that, and I believe in giving you time to process. I'm aware in other classes that your finals come early, and that the degree of consideration and flexibility is just not there. I've never thought that forcing students to take a test early is academically sound. I've made every effort throughout the term to give you plenty of time to do your work, and I will continue to do that. But just make sure that when you set up your time for your final exam, that you are able to complete by 11 p.m. on Friday. So again, I've tried to be consistent with the window of time throughout the term, and I did have to verify with my boss that grades will be due at a certain time that will allow me to give you the flexibility of time by having the test towards the end of the week. So on Wednesday, you can sleep in or rest, do whatever you need to do. I will hold my standard office hours, conference hours that I have done throughout the term. That will not change. And there are many of them. So if you need to take advantage of that, that's fine. And of course, if you need to send WebAssign messages, that will also be good. So just remember, I've had some of you ask about what's the best way to prepare. Well, you prepare by doing the work throughout the term, and that's really how you learn mathematics. But once you have completed your homework, Usually it's good just to go back through the old test and rework the problems. Maybe you don't need to work all of them. Maybe there are certain topics that you have a fairly good mastery of, and it's not going to go south when you see a problem like that again. But go back through the old test. The practice final is basically a summary of the topics, and don't look for the final exam to be overly simple. Don't look for it to be overly difficult. All of the problems will be of a standard nature. And as I've said before, do your work in numeric order and give me complete detail. That is, you don't have to nuance every deduction that you make, but I need to see the work and I need to see your work. And I've been flexible during the term, but on the final exam, I do want to see your work. I do not want to see evidence of homework sites or computer algebra systems. Uh, some of my pre-calculus students will sometimes write an equation down and then bam, there's the answer like magic. Um, that doesn't work. But I haven't had to say this much to you all, but I do want to emphasize the fact that with technology, you have more flexibility. You can use your note cards, you can use your notes. I've always said that is something that you have available to you. And I have said that throughout the term. It will not change for the final exam. But I am serious. Do your own work. Um, we did not have a lockdown browser during this class. I decided against that. So I'm going to leave it to your honor that you do your work. I will remind you, as an undergraduate at the University of North Carolina, every test that we took, we had to sign an honor pledge that we had received nor given any unauthorized aid on the exam that we had just written. And there was an honor court at the University of North Carolina. And I think we didn't live in fear so much, but we respected the academic institution. And when it comes to Sanjak, there is absolutely no difference. We are again in the top 10 of all junior colleges in the nation. And we are waiting to see where we end up this time. I think top 10 is amazing. And we've been in the running for the last 6 or so years, been in the top 10. So the accreditation that you get from San Jacinto College and the fact that we actually do have standards makes a difference. When you receive a degree here, it means something. You earned that degree. And so I've been an ardent supporter of that. And truthfully, no academic situation is going to cover every nuance of an academic career. But you have to realize that when you have a degree, and then you basically have obtained that from an accredited university or college, that is with Southern Association accreditation, that is a benchmark of quality. And so when you go on to complete your engineering degrees or your math degrees or your physics or finance, computer science, you will complete your degrees at accredited universities. And that will be your segue into the professional world. So again, STEM is challenging, STEM is difficult, but just like any career, even if it's non-STEM, the amount of dedication is always required. And as my mom used to always say, and she still does, paying your dues, even though that's the oldest saying in the world, is still very true today. Remember, most of the population now is rethinking their lives after the pandemic. And as we slowly get out of this, that they want to have a better life. And I would want that for anyone. And education is the way to do that. And so now they're going to be even more individuals in STEM. The competition will rise. And necessarily you have to show that you're willing to put in the time. Students, I have said many times that a talent is extremely important. I remember back as a youngster and even in high school when my math teachers would say, well, you need to focus on the math. I know you're a great musician, but you really have ability. And I always told them, I said, there'll come a time when there will be sufficient hours in the day to spend on the mathematics. And so I had to make that commitment at a point in my life where I was going to put in the time, even though the talent was there. The work ethic is what brings you to the next level. So just remember that as you think, wow, life is tough, but it's better to learn that now. I know a lot of you are very young. You're in the early college, high school, and you have started your career as a college student early, and that has great demands, great demands. Back when Professor Ron was a kid, none of this existed, and then we've evolved into it. So take advantage of that, continue to take advantage and move forward. And because you're still so young, reach for that advanced degree. Go on to get that advanced degree while you still have the energy and the momentum. I think you will find it to be very, very rewarding, and also in many ways. Not only, I always say we have these future Bill and Melinda Gates in the STEM classes. You can go on to change the world. So just remember that as you finish up the class. Now, with the final exam, I just wanted to go over a few examples having to do with some of the techniques that have been overriding in the class. And we will start with that right now. So let me share my screen. I'll get this focused, move Professor Ron out of the way. Here we go. Now, like I said before, there are standard constructions that we've done throughout the class, and I want us to make sure that we keep that in mind. For instance, as you're working on problems, and let me adjust this just a little bit so that it's not so angled here. There we go. Now that looks better. Just remember, as you read a problem, you'll be like, oh, that was just like what we had on the last test, or this problem is something we've done a million times. So you're going to find that the problems will be very, very fundamental. So with that said, let's just look at a standard area problem. As I've worked through the exam and constructed the exam, here are the following topics that you will be expected to see. You'll see an inverse trig integral, volume of a solid of revolution, a work example involving moving liquids around. You know, that's the favorite problem and an excellent problem. Integration by parts, trig substitution, partial fractions, improper integration. L'Hopital, maybe in the Cartesian setting or the sequential setting, real series. And usually that will involve conditional absolute convergence, just like you had on the last test, interval of convergence, writing a power series, using series you already know, binomial theorem, things like that. From the newer material, Cartesian, from the parametric, tangent lines, arc length, maybe polar graphs. We've talked about vertical and horizontal tangents, polar area, area of a surface of revolution. That could either be Cartesian or polar, that we have discussed. An area in terms of just standard, what's the area of the region bounded by the curves? And lastly, just a basic trig integral. So what I've done is I've gone through everything, and I've just decided that there are standard earmark terms and subjects that you need to know to be comfortable as you move forward. And I don't want to pad the test with a lot of busy work. So just a little bit longer than the test that you have been taking, but not much. So again, the focus is the standard techniques. So there won't be any curveballs. So don't worry about that occurring. So just as a review, Let's just do a standard area. So compute area bounded by the curves. Students always ask, well, how much information should I put? Just put enough so that I can follow your work, because I go through every problem. Sometimes I wish I had a shorter way to do it, but there is no shorter way. You have to go through every line. So y equals 1/2 x squared, and we have y equals negative x squared plus 6. Now, sometimes the curves will be simple, sometimes they'll have symmetry with respect to an axis. It doesn't really matter. What we found with these types of problems, it's usually fairly simple to figure out, especially when x is independent, which curve is above and which curve is below. So you can use your sketching techniques from college algebra just to kind of put everything into the perspective that makes the confidence level go up. So when you think about curves here, both of these curves will necessarily have to intersect so that we can actually solve this problem. So common sense says the first thing we want to do is just look for intersection. So we can set the ordinates equal. So we'll have 1/2 x squared equals negative x squared plus 6. And if you like, what you can do is you can go ahead and retire the 1/2 by multiplication by 2 if you like. So we get x squared equals negative 2x plus a 12. So now, of course, we can solve this by factoring if you like. So we'll have what, in this particular case, of course, now I've got a square here. So this is going to be a 3x squared. If we take everything over, minus 12 equals 0. So now we can divide by 3 or just factor. And of course, now this will just be x minus 2, x plus 2, which you expected from the symmetry of the curves. So we have a x value of 2 or an x value of negative 2. So now when we look at our points, again, it's not always important to actually sketch this, but if you want to go to that level, you can. So we can say in this case, for 2, we'll have 1/2 2 squared. So this will be 2, 1/2. Well, actually, one of the 2's absorbed, so we just get a 2. So we get 2 comma 2. And then, of course, for the second curve, in this particular, for instance, for the second point, you can use the other curve if you want, but I'll just stick to this one. So we have a negative 2, and then we have a 1/2. Again, negative 2 squared will give us the same output. So this will be a negative 2, 1/2 times a 4, negative 2, 2. So clearly the upper curve is here, but you don't even have to figure out what the vertex is if you don't want. So here we have 2, 2. And we have 2, negative 2. Now, since this is kind of easy, the vertex is simple because this is just a simple transformation. We have a 6, so I'll kind of cheat a little bit. I'll just say that's about a 6. So we got, even though I'm cheating a little. And then we have the lower curve here, vertex at the origin. So again, we've got a nice symmetric region here. So if you like, you can actually take, in this particular case, you've got 2 and -2. You can actually take x from 0 to 2 and multiply the result by 2 to have a lower limit of 0, which we like because it's simple. So we can use symmetry. I like to do problems like this because this covers a lot of bases. It just, all the basic techniques we've been doing from the very beginning. Very simple, but very important. So we'll have area. So we'll just take x to live between 0 and 2. So by symmetry, we'll have 2, 0 to 2, upper curve minus lower curve. So our upper curve is negative x squared plus 6 minus the lower curve, 1/2 x squared dx. And so now we can just do some simple algebra. So here we have a negative x squared and a negative 1/2. So that'll give us a negative 3/2 x squared plus 6 dx. So we have 2. And now we can integrate, add 1, divide by the new power. So we have negative 3/2. Add 1, that gives us a 3. So divide by 3, x cubed plus, of course, 6x, evaluated from 0 to 2. So now we have 2. Of course, the 3's absorb, and we have a negative 1/2 x cubed plus 6x, 0 to 2. So this will give us a 2. And then, of course, the lower limit annihilates both of these. So we have negative 1/2, and we have 2 cubed plus 6 times 2. So now, like we had before, we can just absorb one of these. So this is a 2. So the 2 into here, this will give us 2 copies of 2. So that'll be a negative 4 plus 12. And this leaves us with an 8 inside. So 2 times 8, which is 16. Now, again, when you're working a problem on the test, the level of detail doesn't necessarily have to be as much here. What I wanted to do was just go over some particular aspects. I mean, you can look at this and see that, well, you know which curve is above, you know which curve is below, but this problem opens the door to a lot of nice symmetry, and symmetry is something that can cut down on the amount of arithmetic. And we've seen that in some cases, the arithmetic can be really, really long and time consuming. But what's nice about this is that this sets the stage to any problem where you're revolving. Again, all of the constructs that we have will be in play. I tend not to, as I gave the summary, I really enjoy teaching the center of mass, but that is a specialized topic, and that, as a word to the wise, that will not be covered on the final exam, even though it certainly would be a good problem. It is more specialized. I consider the work problems to be fairly standard, especially in engineering. And of course, when you get to physics, the center of mass will be front and center anyway. But just to kind of give you a heads up about that, that will not be covered on the final, so that you can kind of relieve yourself of that particular technique, even though I'm not saying that it's unimportant. Now, let's look at an example where we actually look at a shell method. Again, these are standard techniques that we spent a lot of time on at the beginning of the course, and they may be a little bit on the rusty side. So let's look at a shell method. In this case, we want to revolve the region revolve region about the y-axis. So whatever the actual axis of revolution is, we just affect our algebra to cover that. So don't look at this as anything but what it is. I think what's important here is that, I want to try to get this more in the center of the IPEVO. There we go. It's important to be able to use the algebra to get us to the finish line, so to speak. So don't worry about anything except if the sketch makes it a little bit easier to see, then by all means do it. Now, the actual region in this case has a boundary by particular curves. So we've got region, in this case, is y equals x squared. We have y equals 6 plus 5x. And then we have the restriction x is greater than or equal to 0. So just like we did before with these types of problems, we'll go ahead and look at the intersection. We obviously have the left endpoint here, so that's done for us. So let's just find the right endpoint. So in this case, we'll just set ordinates equal. So we have x squared equals 5x plus 6. So this gives us x squared minus 5x minus 6 equals 0. So when you look at this, this is a simple factorization. So we can use x. So we've got what, -6, and so we can use -6 and 1. Let me bring the exposure down just a little bit because it looks a little bit flushed. Yeah, there we go. That looks a little better. I can always see, I know I'm probably pickier than you all are. Your eyes are better, but if I can see it well, I know you can. So now we have x equals 6 or x equals -1. And of course, we're not interested in that because of this restriction. So this is the limit that we need. So now, if you will, and it doesn't really matter, we know that the y value is 36, but we don't really care about that. We've got a point, and so when we think about sketching it, we'll just use the liberty of whatever scale gets us where we want to be. So we've got this. So again, in this particular case, this is just review of the shell method, and I always put the shell method on the final exam. It is a standard technique and a very useful technique. So let's just think about the algebraic construction here. And so if you will, we can just have our 6 here, and then of course we'll create a scale here that is useful to us, our 36 here. So we'll have something like this. So we've got our line. Now in this particular case, we see that the y-intercept is 6. So again, I'm cheating a little bit. We'll put the 6 about right there. And then we've got our quadratic. Like this. There we go. That looks a little better. So when you look at this, you're seeing that the shell method is certainly a better way to do this because it's going to cut down on the number of intervals that you will have to compute. So when we look at this and we think about how we want to actually do this, we have revolution about the y-axis. So we need our strip, so to speak, to be parallel. When we actually derived a formula for this, we call it cylindrical shells because we're taking the difference between two right circular cylinders. And the difference gives us that shell or that hoop that we're interested in. So what we can do in this case is let X live between 0 and 6 as we computed here. So we can take an X and just mark in our arbitrary rectangle, so to speak. And now when we look at this, remember we need the height and we need the distance to the axis of revolution. So that's not very difficult. So here, we just usually use the P of X, even though I don't really care what letters you use. This will just be X. And then the height of the strip, or length, if you will just be the upper curve minus the lower curve. So this will be, in this particular case, 5x plus 6 minus, and again, we have our quadratic curve, which is, in this case, x squared. So this gives us 5x plus 6 minus x squared. So now this implies that the volume of the solid of revolution, remember, in this case, we have that concomitant 2 pi, not just the pi, we have the 2 pi with the shell method. And we integrate from 0 to 6. And then we have the distance to the axis of revolution times the length of the strip. And I'll go ahead and write this as negative x squared plus 5x plus 6 dx. And this gives us 2 pi, 0 to 6, negative x cubed plus 5x squared plus a 6x dx. Now, when you actually look at this, this is pretty much how most of our calculations ensue when it comes to these kinds of problems. Just a lot of basic arithmetic. But again, the issue here is just like when we do any calculus 2 problem, all the steps are intertwined. So think about calculus 2 as just doing a bunch of Riemann sums and computing the limit. And then you thought to yourself that if we had to compute all integrals that way, we would lose our minds. So now we can use our power rule. So we have 2 pi. And so this will just be add 1 divided by the new power. So we have x to the 4th divided by 4 plus 5/3 x cubed, that is new power is 3 divided by 3, plus 6x squared divided by 2, evaluate from 0 to 6. So this gives us 2 pi. So we have negative 1/4 x to the 4th plus 5/3 x to the 3rd, and then of course plus a 3 x squared, 0 to 6. Now, don't get used to this, but the lower limit annihilates all of these, so we don't have any difficult computations. Just don't assume that's always the case, especially with trig functions, and then you're like, oh, big issue here. Just don't make assumptions that aren't valid. So now we have 2 pi. So if you will, we're going to have a 6 in squared in all of these. So what we can do is just do a 1/4. And in this case, I will do, let me write it this way. We'll do a 6 squared times a 6 squared plus 5/3, a little dot there if you like, 6 squared times the 6, and then plus 3 times 6 squared, just to make the algebra a little bit easier. So now we have 2 pi, and we've got the common factor here. So let's go ahead and extract that. So that'll be a 36. And so here we have a negative 1/4. And what we can do is just write the 6 squared as 2 times 2 3 times 3. That way we have exact computation to absorb the 4. And then plus 5 thirds. And then we have 2 times 3 to rewrite the 6. And then, of course, we're just left with the lonesome 3 here. So that'll just give us again, I'll go ahead and leave this as it is before I multiply. Let's just kind of see what the numbers look like before we start combining things. And so now notice here the 4 absorbs here, these absorb. So that leaves us with a -9. And here the 3's absorb. And of course that leaves us with a +10 plus a 3. So now basically, if you look here, we have a 4. So we have 2 pi times 36 times a 4. And this will just give us what, our 72 pi times a 4. And then, of course, now we can multiply. So that'll be an 8 and then a 28 pi. So again, when it comes to the shell method and working with liquids and things like that, the setup is all the same. And so this is the part of the test that you will find maybe a little bit rusty because it's been a while since we've been focused on this. We've done a lot of arithmetic and algebra, but lately we've just been doing a lot of trig. So what you'll find is that the stuff that we just did is right fresh on the mind, whereas the older material, you've got to think a little bit more about. So when you're actually doing review, go back through these very standard calculations, albeit not very difficult now. You can see that at the time it's like, this got kind of tedious, but what we're seeing is that compared to what we've been doing, this all makes perfect sense now and maybe doesn't seem as bad as it was at the time. So let's, again, as you review, just make sure that you take the time to go over things that are just in the past, first and second tests that may have become a little bit rusty. I always remembered, even in grad school, make sure you know the new stuff, study the new stuff, get that down, and then go back to the earliest test to review. If you've committed everything to long-term memory, you don't have anything to worry about, but I know that's not true. So it's better just to go ahead and work it out. Now, one of my favorite types of problems has to do with the integration techniques. Remember, with the final exam, you just kind of get one of everything. And so you might have some definite integrals. You may have to evaluate some trig functions and things like that, partial fractions, things of that nature. Again, if there is a definite integral, I need to see the computation of the antiderivative, and I need to see the evaluation beyond just writing down an answer. So again, those types of problems just cover the fundamentals. So just remember that those problems will not be overly difficult. You just have to go back and rely on your college algebra and your trig, which I think we figured out is kind of the linchpin of calculus 2. Now here's a simple example of an integration. Now in some cases, I may make a suggestion about how you integrate or whatever. If it says, use a particular method, I want to see that. If like it says use shell method, I want to see the shell method. But if nothing is said about whatever, then you can use what you feel is most straightforward. So when we look at an example like this, we're thinking, okay, well, this is just, I think what I'm going to try to do is make sure I put problems for the integration by parts where you actually have to use it. Sometimes you can use miscellaneous substitution and, get the same answer. And even though they look a little bit different, The idea here is that when we look at this, these are disparate in the sense that this is algebraic and this is transcendental. So if we wanted to compute this antiderivative, then we would definitely need to use integration by parts. So at this point, this will require more than one application, so you can actually set up the table as I've taught you to make the computation very straightforward. So this is just review of integration by parts. And of course, that's probably one of our most, I would say, useful integration techniques. So now, of course, the way to make the problem simple is that since this is a polynomial, we would prefer to differentiate this to bring it down to 0, and then of course integrate the e to the x, which we can do in our sleep. So again, you don't have to worry about the u's and the dv's. That's taken care of, and it cuts down on the amount of notation. So remember when we think of integration by parts, we have u dv integral is equal to uv minus the integral v du. And the idea is that when we look at this integral, we may have to apply integration by parts again. And so the idea is that when we have this, if we look at our row that we generate, then we have the selection of a new u and the selection of a new dv without having to rewrite the step. And that's where this procedure is very useful. And I think now you know that, but it doesn't hurt to remind yourself why it is actually valid. So now this gives us a 2x minus a 6, and of course e to the x. Now we have a new u and a new dv, and of course we would need to apply integration by parts again because this would be just like the first one. So upon application of that, we're going to get a 2 e to the x. Now, of course, you're thinking when you run across this way, that's just a simple integral and no need to worry about it. Well, the integration by parts says just go ahead and finish the problem and you don't have to do any integrals at all, at least in an overt way. So now we have the 0 and then the e to the x. And so now, of course, moving across would just give us 0. So the idea is that the process is terminated once we get to this point. So this method is very useful. And as we've seen in doing the Laplace transform that I introduced to you, extremely efficient in keeping up with signs. So now we can go ahead and do our diagonal lines and alternate the signs. So we have a plus minus that we get from the integration by parts, and then we have a minus minus that turns into a plus. Now, of course, when you've got signs running all over the place, this is very helpful. And again, this is multiplicative. So now by integration by parts, we first see we have e to the x, and we've got x squared minus 6x. Now we have minus e to the x, 2x minus 6. And then lastly, we just have 2 times e to the x. And then, of course, the concomitant integration. Now, when you think about all of this and you think about what we're doing, what's important, it's not so much that we look at this from the standpoint of how can we do this most quickly. We look at this from the standpoint that we're applying a technique in this particular case 3 times, where the third time we don't really need to do it, but we do it anyway because we're lazy. So when we actually affect this, be sure to use this if it applies. And then even if you only have one pass, it still allows you to organize your work well. So now we can just go ahead and we've got e to the x's and everything, right? So we have e to the x. So we've got x squared minus 6x minus a 2x Now here we've got minus minus, so we have plus a 6, and then we have plus a 2. So we have e to the x, and then we can just combine terms. We have an x squared minus an 8x plus 8 plus a constant. Now, of course, if we had limits of integration, these would be easy to apply here, but this technique kind of covers how this particular structure of organization is very good. When you think about it, no matter how many passes you have to do, it organizes the signs. It allows you to have a easy way to check your work, and that's really important. So keep that in mind as you work through these types of problems. Now, the next example, again, we've done a lot of work with Pythagorean identities, and I'll always say, like I was going through trig sub with the triangles, very useful technique, just the basic trig integrals, using the basic Pythagorean identities. Again, seem very simple and straightforward. So as you work these problems, just relax, just kick back and just say, okay, this is nice and straightforward. I'm just using the calculus I learned in Cal 1, and I'm using my Pythagorean identities from pre-cal, and keep it simple. So, and of course, I will stick to the more fundamental examples. So let's look at this one. 0 pi over 3, tangent x. These are always fun examples. So when you see a problem like this, you know, we usually cringe when we see the trig integrals, just because we're thinking, if we got even powers of sine and cosine, oh, I'll use the reduction formula, or I'll use the power reducing identity and just reduce the algebra. Again, there are all kinds of nice trig integrals that you're going to see as you continue your work in STEM. And you don't have to memorize anything. You just have to go back to the basic identities. But now this is a common construction that you see. Notice we have the derivative of secant is the secant tangent, which we can easily construct from this integrand. So like I said before, we appeal to the calculus we learned in Cal 1 and drive it forward. So maybe, like I say before, you could have done this in Cal 1, but there's only so much time during the term. So basically, lots of the techniques we've learned in Cal 2, we just borrowed from Cal 1 and just extended the construct. So let's do that. So again, we'll have 0 to pi over 3, and we'll just write this as a secant cubed. And we don't have any differentials to worry about, and we can write this as secant x tangent x dx. So now, of course, we have the power rule. We have the u raised to the third power, and then we have the du. So this is table ready, which I guess I've overused too much. And so now we just add 1 divided by the new power. So this will be 1/4. So again, use Cal 1 results. We do the parametric. We use a lot of the Cal 1 derivatives, especially derivative of tangent, derivative of secant, all of those, they just run right through the calculations. So we get what? Secant to the 4th x, 0 to pi over 3. So now, of course, we have 1/4. So we have secant of pi over 3 raised to the 4th power minus secant of 0 raised to the 4th power. So this is what I was talking about before. This is not 0, you know, of course, and it's easy to forget it when you're trying to move forward quickly. So this is what I was talking about before. So we have 1/4. And of course, now secant of pi over 3 is 2. It's just the reciprocal of cosine. So we have 2 to the 4th minus 1 to the 4th secant of 0 being 1. So this is 1/4, 16 minus 1. So we get 1/4 times 15, or 15 over 4. So again, when it comes to the work that we do with basic integrals, and now I'll call them all basic, unless I specify a particular technique you can use. In most cases, the technique that I specify will be the one that you need to use, not that I just necessarily want to see the technique. But yeah, if I recommend something, I want you to use it. Otherwise, you can use whatever technique you like. Now, when it comes to working partial fraction decomposition, just remember that if you have a situation where the degree, if you've got a rational expression and the degree of the numerator is larger, first you need to divide to reduce it, because that's really a calculus 1 integral. Okay, so if you got that degree set up, then reduce and then apply your partial fractions. So if we look at an example here, and I like to test on that just to make sure that you're being aware of that. So divide if you need to, if you've got a larger power in the numerator, because that'll just produce polynomials, which you can, very simply integrate. And then the residue, or the residual part, will be the rational expression to which you apply the partial fraction decomposition. So here's a very straightforward example. So, and of course, remember repeated factors. That's also very important. I tend to test on that also. So if you were just asked to integrate this, then you're thinking, well, the partial fraction would work, and basically you're going to get two distinct linear factors. But this is what I was saying before: the degree in the numerator is 1, the degree downstairs is 2, so there would be no need to divide. Okay, so if they're equal, or the degree of the numerator is greater, then you must divide first. Otherwise, your technique will fall apart. So now first, what we can do, and also remember our techniques for improper. Lots of times the improper integrals and the partial fractions work very nice together. So we have 5x minus 7. And then of course downstairs we can use a -5 and a 1. Remember on the test where we had the nice integration by parts, or we had the partial fractions, and then you had to rig the integral. Those problems are very fun and interesting to do, but on the final I'll tend to hit more of the fundamental constructs so that you have time to finish the test. So at this point, we look at this and say we would need to actually deconstruct this rational expression so that we could actually integrate it. So someone actually at one point in time got a common denominator, which was x minus 5 times x plus 1, and we're thinking all in good. But now we need to go back. We need to be investigators to say what was the case before you got the common denominator. So again, just to remind you what we do with partial fraction decomposition. So now we've got two distinct linear factors. So we have 5x minus 7 divided by x minus 5 times x plus 1. And since these are linear factors, we can just say a divided by x minus 5 plus b divided by x plus 1. Now, of course, we're lazy, so we want to clear denominators. So we're going to multiply through by x minus 5 times x plus 1 to get an equation that's true for all real numbers. So we have 5 minus x equals a times x plus 1 plus b times x minus 5. So now, of course, since we don't have to differentiate in this case, differentiation is a tremendous technique, but here we can just use some very convenient values of x. So we have x equals -1 to annihilate the term with the a. So we get 5 times a -1 minus 7, and that'll just be a 5 plus a 7 with a negative, so that's a -12, equals b times -1 minus 5, which gives us a -6b. Of course, the negatives absorb, and we get b equals 2. And now, of course, we'll use the same technique here to find a if we can substitute x equal 5 here. So x equals 5. Again, how much time we do here just depends on how complicated the expression is. It's the same work, no different. Just may take a little bit longer. So x equals 5. So we have 5 times 5 minus 7. So this is 25 minus 7. That gives us an 18. This is annihilated, and so we have a 5 plus a 1, which is 6a. And now, of course, 6 divides 18 3 times, so a equals 3. And then, of course, you're thinking if you start differentiating here, it doesn't really help you that much. And of course, when you take differential equations and you learn method of undetermined coefficients, you're going to probably not like it a whole lot, but it's okay. There's certain techniques that are similar to this, and other techniques that just seem to be long-winded. And unfortunately, that's the case. So yeah, like Professor Ron, right? So now when we see here, we've got our coefficients. So this implies that the integral 5x minus 7 divided by x squared minus 4x minus 5, just like we were doing an improper integral, this will be the integral of this expression where we have the a's and the b's. So we have 3 over x minus 5 plus 2 over x plus 1 dx. And so now when we actually look at this, we can integrate this by linearity. So this will be 3 dx over x minus 5 plus 2 dx over x plus 1. And this will give us 3 times the natural log of the absolute value of x minus 5 plus 2 times the natural log of x plus 1 plus a constant. So again, just remember all of the pitfalls of partial fraction decomposition. If you have repeated factors, then you have to ascend to that repeated factor. Linears are always the constants. The quadratics have the linear ax plus b. Just basic techniques, and do all the things that you think about that you would do in college algebra in Cal 1 to make the process simple. Now, one thing that's kind of interesting here is that I always like to throw in a improper integral, because that's a basic technique that you'll use in your transform techniques. And I always refer to differential equations, and even in engineering. So of course, that means that you can have an infinite limit, or that means you can have a infinite discontinuity in the integrand, or even both. So what I'll probably tend to do is to focus on one of those techniques. So here's an example. So again, we'll have the integral from 0 to 2 of dx. Of course, the inverse sine form is very useful and comes up quite a bit. We see that as we learn the parametric representations, all the calculus just floods back. And we have a way to compute a Cartesian derivative from the parametric representation, which we have used continuously, even when we got to polar coordinates. So all of this will pay off handsomely in Calculus 3. Just remember that these techniques will be used just probably not so much early on, but as you get to the differentiation, partial differentiation, and then into the integration techniques, and of course the vector calculus theorems, you'll find them to be very useful. Now, of course, this kind of reminds us of the arc length problem we did the last time. Remember I said the problem is in the denominator, we get a 0, and then when we integrate, the problem is removed because the radical moves into the numerator, just like we saw with the arc length calculation that we did at our last lecture. And that, my friends, was complicated in the sense that there was plenty of work to do. Not all the problems will be as tedious as that. Some problems on the final will be like, well, just knock it out, not even difficult. Others, you may have to do a little bit more arithmetic, but all of the problems will be very standard techniques. And so just approach the problems that way. Don't worry about trying to finish them quickly, just work through them. And I think you'll find that you will arrive at the correct response. So now when we look at this, like I said before, this is just like the problem we did at the last lecture, because we see at 2 here, we have an issue. So if we want to write this out formally, we've got our 0 here, and then we can have our 2 here when we're actually approaching from the left. So we basically get an infinite discontinuity. But we see that upon application of the fundamental theorem, that issue will become in the past, so to speak. And again, we see this often. You can almost look at something and say, well, we can repair this with the definition and get to a convergence. And usually your intuition is correct, but don't think that, well, it's a lost cause. Let the computation ensue and don't jump to the finish line too soon. The problem is that if you try to predict the future too soon, it will taint your calculations and force errors that you don't intend. So now we can see in this particular case that we have the limit as b approaches 2 here from the left. Use whatever letters you like. I tend to use the A's and the B's. Just make sure your B looks like a B and not a 6. So there we go, B. So now we've got the integral here, 0 to b of dx square root 4 minus x squared. Now, of course, before we just did the add 1 divided by the new power, but we see this is the arc sign. So in this particular case, a is equal to 2 and the u equals x. So that's easy, okay? So now we apply the anti-differentiation technique. So we have the limit as b approaches 2 from the left. And this will give us the inverse sine of, in this case, x divided by 2. We learned that the very first week of class, 0 to b. So now we apply the fundamental theorem. We have the limit as b approaches 2 from the left. So we have inverse sine of b divided by 2 minus inverse sine, and of course we substitute 0, we get 0, inverse sine of 0. So now we can apply the limiting process here. We can just move the limiting process inside if you like, but now this will give us, in this case, when we apply the limit, let me write it one more time. So this will be the limit as b approaches 2 from the left of the inverse sine of b over 2. And of course, that's just 0. So we can move the limiting process inside, and this will just give us inverse sine. B approaches 2 from the left. That just gives us inverse sine of 2 over 2, which is inverse sine in this case of 1. And we get what? Pi over 2. So like I said before, don't rush to the finish line too soon. Just let the work play out. And of course, the inverse trig integral forms are such use to us. The nice thing is that these come up all the time and usually make our calculations simpler. So again, this is a little bit more complicated than the problem we did last lecture, but again, utilizing techniques that you know. So don't expect a problem to be hard. Just expect it to be focusing on techniques that you know how to do, and you don't really know what it's going to be until you actually look at it, right? Now, one thing that's interesting about what we've been doing is that we have L'Hopital's rule. You know, we can use that with the improper integrals. We can use that with our sequences, and understand indeterminate forms. We now know that when you get 0 over 0 or infinity over infinity, that's not 1. We would love it to be 1. And so we just remember, if you need to apply the L'Hopital, then do it. And again, in very straightforward situations, it'll be easy to figure out. We spend a lot of time on L'Hopital. It'll be easy to figure out the indeterminate form. Now, just kind of going back to some of the series, again, with the polar coordinates and all of that, since I've just beaten you up about that, I think you understand that pretty well. So that you've got in your brain. I just don't want you to forget the old stuff. So now when we look at this example, we've got the following series: k equals 0 to infinity of cosine k pi divided by 3 to the k. And here we'll just say determine convergence or divergence. And then we'll just say if convergent. So this is kind of a loaded question. If convergent, compute the sum. So a lot of times students will look at these and say, well, I don't know, Professor Ron, and this is where you appeal to your pre-calculus studies. So now notice we've got this interesting numerator here, which is just the cosine function. But remember, for instance, when we just test a few of these things, we'll just do k equals 0. So we have cosine of 0, which is 1. And then we have k equals 1. And we have cosine of pi, which is -1. And then we have k equals 2. We have cosine of 2 pi, again, which is 1. The idea here is that we're just moving along the x-axis when we think about the unit circle, from the positive x-axis to the negative x-axis, multiples of pi. So that either puts us positive x-axis or negative. That is, we oscillate back and forth. And so upon doing that, we get the 1 value, we get the -1 value, we get the oscillating values here. So this would imply that cosine of k pi can just be replaced, if we think about this, -1 to the k. And of course, this would be in alignment. When k is equal to 0, by definition, we get 1. When k is 1, we get -1, etc. So what we see here is that we get a very simple series that looks rather ominous when we first look at it. So again, when you look at these series, just like the last test, take a little bit of time to break it down before you just surge into it. And then you might say, well, when you look at this, this is not, remember, this is not absolute convergence, conditional, or whatever. So when you've got a problem where it says, if it converges, I want the sum, give the sum, you can't find the sum of the absolute values. That's not the question. So it's really important to answer the question. Okay. So don't, don't jump to the finish line too soon. That usually is an issue when you're doing calculus problems. We're like, oh, I got it, I got it. Well, no, you don't. You just let the problem work itself out. So now this gives us, from this elementary analysis, k equals 0 to infinity. And so we have -1 to the k, and we have 3 to the k. Now, of course, we have our laws of exponents, which couldn't do very much with series without it, without them, that is. So this will be a -1/3 to the k. Now, when you look at this, this is just a geometric series. Now, one thing that's interesting about this, if you think about the way I derived all of this, this looks like the 1/1 minus x, okay? But when we did our derivation, you know, this was a k minus 1 and we started at 1. So however you want to write it is certainly up to you. But just make sure whatever construction you use, it abides by the form that you've written on the page. So just recall, if we just want to stick with this, recall, and this is what we use all the time. Once we relaxed our notation, we know that 1/1 minus x equals this series. And this will be a good series to use on your final exam. This is just x to the n. So we'll apply this directly since this form fits exactly, okay? So now we've got what? X is -1/3. So we have 1/1 minus -1/3. So this just gives us 1/1 plus 1/3, which is 1 divided by 4/3. And we reciprocate that and get 3/4. So problems like this don't take a lot of time. It's not like you're doing an interval of convergence and you've got to work, you've got to work to find the, open interval and then test the endpoints. And that can require, again, figuring out, okay, what's the deal at the endpoints, and you don't always want to assume that. In some cases you do, because you've got to move forward because time is becoming important to you. So the example that's next is actually very important. That tends to be one that students confound a little bit. I don't, if you're still struggling with series, go back through the last test and the third test and work through the examples and make sure you understand that there are some cases where the understanding of what a series is not actually there yet. And I don't want you to miss the same types of problems over and over. So make sure you go back to the beginning and kind of build the foundation so that you understand that a real series is just a sequence of partial sums. And so when we apply the convergence test, we're simply just applying a recipe, okay? So don't make assumptions about the series that aren't true. If it seems wrong, it probably is, okay, when it comes to infinite series. So here's an example. And here's a good example. So we have k equals 1 or n, whatever, doesn't matter what letter you use, 2k. We have k squared plus 4. Now, when you look at this and you think about this, and this is a technique I've shown you many times. So let me click the focus. There we go. When we look at this and we think about, what's going on here in terms of basically what I'm saying, when we think about this, what's happening to this nth term, this generating term, as k becomes really large. So as an aside here, we say 2k over k squared. And you can do this many different ways. There's no one way to do this. We can just say this is approximately, that is, the 4 is not really going to have much of an impact. This is going to be approximately 2k divided by k squared, which is 2 over k for large N. Now, this is the kind of analysis that makes sense when you're looking at this, because this is a positive term series. And what's nice about it is that because it's so straightforward, you can say, well, when k is large, it's really reacting more like this. And this is basically the strategy behind the comparison test. The direct comparison test is very powerful, but the limit comparison test is easier to use. And so when we look at this, we're thinking, okay, well, we can compare this series to this series because basically at infinity, they're doing, the nth terms are pretty much doing the same thing. And then we just say, observe that the series k equals 1. Now, sometimes we have to use the integral test. That takes a little bit longer. You all don't like the integral test. You don't like to validate the hypotheses, and that's unfortunate. But this is just what 2 k equals 1 to infinity of 1 over k, which is a very famous divergent series. This is infinity. This is divergent. That's what we learned from the integral test way back. So now what we want to do is we'll set a to the n equal 2k. Well, I guess now that we're using k's, I'll use k's. B to the 2 to the a to the k, and then b to the k, right? So a to the k is 2k, k squared plus 4. And b to the k, we can just take to be this guy, 2 over k. And of course, it doesn't matter if you leave the 2 there or not, the same result will ensue. So now we have the limit as k tends to infinity of a sub k divided by b sub k. So we have the limit as k tends to infinity. So we have 2k, k squared plus 4. And then, of course, when we reciprocate, we just, in this case, this will give us a k divided by 2. So now we've got the limit as k tends to infinity of 2k squared divided by 2 times k squared plus 4. So now, of course, the 2's absorb. So this is nice if you choose to put the 2 in it. You don't have to. So this gives us the limit as k tends to infinity of k squared over k squared plus 4. And now, of course, we're kind of back to the initial analysis. As k tends to infinity, we've got the leading coefficients here because of the fact that the degrees are the same. So at infinity, and this is what you prove in Calculus 1, this limit would be 1. And this is clearly bigger than 0. So whatever this series does, this must do the same. So then the given series k equals 1 to infinity of 2k over k squared plus 4 diverges by limit comparison test. Now on the final, I want to see an improvement in the analysis of this. I spent a lot of time working through this. I'm very thorough on everything. And I think sometimes in mathematics, everybody thinks that there just should be a simple way to memorize. Folks, memorization is not going to be the key to success in STEM mathematics anymore. You have to understand it. You need to have your formula cards because I think that keeps your anxiety down. And that's important. I don't want you to miss a problem. You can use your integral tables, especially if the problem is not just an integral. If I want to see a technique and you integrate, then that's fine. But the thing is that you have to supply the the foundation of what you're doing. I don't care that if you're doing a bigger problem and you use the integral table like you're doing an improper integral or something, and it makes sense to do it, and then you pass to the limit using the identities of the logarithms. That again is kind of what's part here. So take a little bit of time to make sure this makes sense. You all do such good work, and then sometimes you just miss small analyses that I think you could easily do. Again, it's not a matter of putting so much more time in it. It's just a matter of focusing on a couple of simple techniques and disposing of it and moving forward. Now, you know, I'm a big fan of the binomial series. So of course there's going to be one of those. So let's just look at and then of course the geometric. Remember, with the geometric form, you can integrate term by term, differentiate. I would say it's time for a differentiation example. So just like the one I did with the probability, with the expected value and how we use the derivative to get that nice form, things like that are very useful. Now, here's an example. You can expect one with the binomial series. These are my favorites. And of course, some of you, like I did on the last test, you can actually write a general series, but if the problem doesn't request the general series like you had in some of your homework, you can just work out the coefficients. And again, this will be part of the test. So here's an example. So in this case, this says, let's see, 1, 2, 3, 4. It says compute the first 4 non-zero terms. So this is where you're using your techniques from your chart of series, or techniques based on a particular series form. Compute the first 4 non-zero terms of the Maclaurin series and maybe it just says series. You're obviously going to be Maclaurin series for f of x. Now, again, if you used your chart, you can say, well, this is binomial. This is binomial. And of course, here, the new x is x over 4. So we can say this will give us, so we'll say binomial series. Of course, I'm not going to give you a positive integer here. That would be a waste of time. That's not even worth your time. Well, it is in pre-cal, but now you've elevated yourself. So now we have n equals 0 to infinity, and we have -2. You're thinking, where's the fraction? Thank you, Professor Ron. So don't count on it, but we should be able to do this. Choose n. And then we have x over 4 to the n. Now, of course, as I said before, to make the computations a little bit easier, the first coefficient's always just going to be a 1. So you might as well go ahead and write that out by definition. So this is 1 plus n equals 1 to infinity, -2 over n. And then we have x to the n, 4 to the n. Now, of course, in this particular example, you don't have to worry about giving me a general form. So just go ahead and compute coefficients. And I think that would be the quickest way to do it. So now first we observe, we've already got this one. This is just n equals 0. So that's a check. That is -2, choose 0 by definition is just 1. And so that's the first term when we're doing the binomial series like this. And then of course we have -2, choose 1 is just -2. So that's quick. And then we have -2, choose 2. So this will be -2 and then -2 minus 1. divided by 2 factorial. So this is what? Negative 2 times negative 3 divided by 2. Okay, the 2's absorbed, so that gives us a positive 3. So again, when you look at problems like this and you think, okay, you can generate the actual coefficient with the general series, or you can do it this way. And I think this will be a little bit quicker when you're trying to move through the final exam. And then, of course, we have negative 2, choose 3. So this will be negative 2 minus 1, negative 2 minus 2, divided by 3 factorial. So here we have negative 2. Well, of course, if you want to kind of shortchange just as a matter of efficiency here, I won't do that because that'll just be confusing. Let me just write this out, negative 3. And then you have a negative 4. You have a really nice string of factors here that don't leave out anything, which is kind of neat when you don't have the fraction here. So that's a plus. And then, of course, you have what? 2 times 3. And now, of course, these absorb. And you're left with the negative 4. So I think you may find this to be a little bit quicker if you had this type of problem on your final exam. So now we can just fill everything in. So this is 1. Then we have plus. So we have n equals 1. So let's just go ahead and fill this in. So this is a negative 2. And then we have x over 4. Then we have plus n equals 2. So we've done this. We go here. So we have 3. And then we have x squared over 4 squared. And then n equals 3. Down here, we have negative 4. And then we have x to the third over 4 to the third. Hopefully now you're appreciating the infinite series and the power series are just the fancy arithmetic that has always been, behind the scenes, so to speak. There's nothing about the real series and power series that goes beyond any strategies that you've ever done before. We just need the calculus to bring the arithmetic in together with the theory so that we know how to use the correct arithmetic. But now hopefully you're developing a much better feel for calculus, that it is just a refined arithmetic, and that's all we have ever been doing. So now what do we get? We get 1, so we get a negative 2 over 4, so that's a minus 1/2 x. Here we just get a 3 over 16. And then, of course, the 4's absorb here, and that'll give us a negative 1 over 16. So that will give us our first 4 terms, and of course, whatever the series after that. So again, feel free to do whatever, but if you just have to generate, depending on what the problem asks you to do, this may be the quicker method. And this really just reminds you of what you did in calculus and pre-calculus. The interesting thing is that when it comes to the series, I like it how some of you just said, well, the heck with this. I'm just going to use the Taylor coefficients and I don't care, because Professor Ron said it would work. And that's true. I mean, you don't have to do any of this or specialize anything. That will always work. But sometimes these techniques are maybe easy to remember, but I guess the Taylor's theorem is just boom, it's always there when you need it. How funny. Okay, so now what I wanted to say a little bit about are some of the constructions that we do. We've done that long arc length problem, so I won't worry about that, but I'm going to give you a situation where you, for instance, will write an equivalent Cartesian equation. That'll just be a basic example. I'll have a problem where probably you'll need to do like the vertical or horizontal tangents, and I'll ask you the points and I'll tell you how I want you to write them, if they're polar or Cartesian, something simple like that. And probably an arc length problem, that could be Cartesian or polar. But just to kind of remind you about what we're doing here, for instance, here's a simple example. And we've done a lot of work with these, and I want to work through an area problem too, just to kind of give you an idea about that. So here's, yeah, let's do this first, and then we'll do the area problem. So we've got r squared. In this case, let me see here. Let me pull this up to see basically how it's stated on the practice final, because I don't want to write it down incorrectly. Let's see here. Yeah, here's the form. Let me write this down. So this is r squared sine 2 theta equals 24. Okay. So let me go back here. Good. So this is the polar equation. Polar equation. And we'll say write. And this is where sometimes, remember all the polar curves that are simpler, written polar, whereas there might be curves that aren't so simple in polar, but we need, when we did the torus example and we had the line x equal b written in terms of the polar equation, so we could use the polar construct. Well, that was a little bit untoward. And sometimes we're like, that's so silly. But if we're using a particular coordinate system, we can always just replace x with r cosine theta or y with r sine theta and work it however we want. Even though it may seem a little bit crazy, it will still provide us what we need algebraically. So here we want to write the equivalent Cartesian equation. And I remember we did that nice area calculation last time, that with where we had the 4 petal rows in the circle. That was a problem that never quit, right? So now when we look at this, we can say, okay, let's go ahead and use our trig identities. So equivalently, we have what? R squared, and then we have 2 sine theta cosine theta equals 24. Now, when you think about this and you consider what we're doing here, you might think, okay, well, r squared is just what? X squared plus y squared. And we can go ahead and work with that. But now we can rearrange things a little bit. Let's rearrange. So if you like, let's go ahead and spread the wealth, as they say. Here's another way of looking at it. So we've got 2 here. And well, we've got a 2 here. Let's just absorb it. So let's absorb this. I don't like having things hang around. So that's absorbed. And now let's spread this r out. So this is r. There's even a simpler way to look at it. It's funny because math is always evolving. And as I do my own research, I think about the fact that as you look at a problem, once you fixate on the technique, you stick with it. You don't start running around unless you're like, oh man, I didn't see that. I've only done a little bit. Let me do this. That's going to make this problem a lot quicker. So if you look at this, notice I made the comment about the x squared plus y squared, but notice we can just spread the r out with the sine and the cosine. And now, of course, by definition, this is just y, and this is just x, and we're done. So the key here is that it doesn't matter how you do it. It just basically evolves in a situation where you're thinking, okay, if I want to write everything in terms of R's, like here, you can think about this and write this as X over R, Y over R, and X over R and accomplish the same thing. Doesn't matter. It doesn't really matter how you move to the finish line as long as you're executing good mathematics. So this is just kind of a simpler way to look at it, but certainly no better than any other technique. So we get this, these conjugate hyperbolas. That is, now we have y equals 12 over x. Now, of course, it might be convenient to write it this way depending on the calculations you're doing, because you know what this looks like. This is just college algebra. But now that you're smart and more educated, and you have gotten smarter, that's true. As you build your foundation in STEM, you do get smarter. As I've said before, there was a time when experts thought that the IQ was stagnant. That is clearly false. When I went to grad school, I had done a lot of preparation. My IQ went up, and then of course when I finished grad school, it went up. So the more STEM you do, the brighter you're going to get. You might be tired, and people think, well, you're kind of slow these days. It's like, well, no, I'm just tired from doing mathematics. But yeah, it does get better. So keep that in mind as you continue to work. So we get something like this. These are like conjugate hyperbolas. This is a rotated hyperbola. That is 12 equal xy. That's the cross product term, which you usually never have time to do in pre-cal because you're so busy trying to finish all the work. I taught the rotation term last time I did an honors pre-calgebra course, and I will do that in the fall. But again, when you look at this is just a rotated hyperbola. So you think about this, it may be convenient to actually write it this way because you can always take this backwards and get right back up to here. So everything's connected. I know that's overused, but everything's connected. Now, the areas you're doing fine with, but there's a calculation here that I like. Say, for instance, you're doing some tangents, and you've got to, if you're doing tangents, vertical tangents, horizontal, you compute x prime and y prime, and you find when they're zero. And if you've got two values of the parameter that give you the same value, they're both zero at the same time or whatever, you get rid of that. That's a cusp. So that we've talked about. But say you're just asked to compute a Cartesian derivative. And what I want to do here is just a simple calculation of a Cartesian derivative, which kind of innervates the vertical tangents, horizontal tangents, that innervates all the formulas that we used when we derived the arc length formula and the area of the surface. So here's an example. I thought this was an interesting problem. So you've got this polar curve here. So this is kind of the linchpin that's been behind all of our new formulas. So go over the problems that I did in the last lecture because those are extremely important. And just remember, you only have 20 problems, so that's a luxury. I think the shortest test I've ever given in Cal 2 was 25 or more, and I'm going to improve upon that. So we have R equals 3 cosine 3 theta. That's a rose curve. And then we have theta equals pi over 3. And the question is, in this particular case, compute, and let me make sure I state it just the way it is on the exam. Find the slope of the polar curve. So basically this just says compute dy dx at theta equal pi over 3. So this is kind of a crazy thing in the sense that when you look at it and you think about it, first you're saying, okay, I've got to do a Cartesian derivative, and so I've got to map everything just like we did before. And so let's do it. So now x equals r cosine theta. So we have, let's just take this. So we've got 3 cosine 3 theta times cosine theta. This is just a good computational example. And y equals r sine theta. You don't have to memorize this. I don't want you to. So r sine theta. So this gives us 3 cosine 3 theta times sine theta. And so now let's go ahead and compute the derivatives. So we have, in this case, I'll do y prime first. So we've got this. So we have 3. We have what? The derivative here, so that'll be a negative sine 3 theta. So the derivative of cosine is negative sine times the derivative of the inside, which is 3, times sine theta, plus 3 cosine 3 theta times cosine theta. So this is one of these problems that just keeps on giving. So this will give us what? A negative 9 sine 3 theta sine theta. And I thought I'd do this one because it has the multiple angles, so that makes a good computation. And then for x prime, that's this one. So again, we've got 3. Again, the derivative of cosine is negative sine, so we have negative 3 sine 3 theta times the derivative of 3 theta, which is 3 cosine theta. Now we have minus 3 cosine 3 theta, the derivative of cosine negative sine theta. So now we can write this down. So we've got what? Negative 9 sine 3 theta cosine theta minus 3 cosine 3 theta sine theta. Now, this is kind of a busy work problem, but again, if you're going to do vertical tangents, and I'll set it up so that you don't have this much complication so you can actually solve the equations. But I like this problem because it simply attests to the transformation here. And so now if you like, we know that dy dx is just y prime divided by x prime differentiated with respect to the parameter. So now if you like, you can just go ahead and evaluate each of these separately and then take the ratio. So now this implies, and I'll just say here, theta equal pi over 3. So I'll just go ahead and stick these in, pi over 3, pi over 3, right there. Okay? So now we have what? Y prime of pi over 3. That'll give us a negative 3. So this gives us sine. Okay, now pi over 3, the 3 is absorbed, so that's a sine of pi times sine of pi over 3. Plus, now we have the 3 absorbs the 3, so we have 3 cosine pi times cosine pi over 3. So of course, this is a 0, so we have negative 3 times a 0. And here we have plus 3 times a negative 1. And here we have a 1/2. So this gives us negative 3/2 for the y prime. And then x prime. So now we go here. So we've got, let's see here. Let's see, everything looking good. Yeah, so now I was just making sure I did the correct line. When I did here, I did the sine, the cosine. Yes, now we'll do this line. So we have negative in this case. I think what I did here is I looked at it. I looked at it right up here. So I'm just trying to make sure when I did the negative here, I just kind of avoided that. So let me just write it correctly. We got the negative here. That's the -9 here. So let me just write it correctly, even though it zeroes out. So this one I did right here. So we have the -9 sine, then the sine, and then the 3 cosine, cosine. So that's the one there. So that looks good. And so now for this one, we have -9 sine of pi. Again, the 3's absorb, cosine pi, minus 3 cosine. Here again, the 3's absorb, and we get pi. And then we have sine of what? Pi over 3. So this is one here. So now, of course, here, let me go ahead and put the right coefficient there. So we have -9. Of course, that'll be a 0, so times a 0. Minus 3, -1. And then we have sine of pi over 3, which is √3 over 2. So we have minus a negative. So this is 3√3 divided by 2. So now we can take the ratio. So this implies the slope of the polar curve using the Cartesian at theta equals pi over 3 equals y prime of pi over 3. This is just a fun problem because it's just got a lot of arithmetic in it. That's the only thing, just to give you some practice. You'll use this on the final, but you won't have the multiple argument there. But I thought this was an excellent example and just extra work, but not difficult work. And so now we have y prime. So this is a -3/2. And now, of course, here we divide by this so we can reciprocate. So we get 2, 3, √3. The 2's absorb. The 3's absorb. And we just get -1 over √3. So the thing that I want to focus on here, I mean, you can evaluate functions. That you don't need me for that. I mean, you all are very wise and you've had plenty of training if you got to Cal 2. The main thing is that all the work that we did calculus wise with the parametric representation, then we think of the polar coordinate representation. We start with the polar coordinates, we define them, we spent time graphing them. You probably got tired of that. The graphs are easy when you do the Cartesian and work backwards. I mean, that's a very elegant way to do it. We even did the figure 8. But calculus wise, to move from the polar coordinates to the parametric, we have to use this transformation here, which we basically set up when we defined the polar coordinates. But then we know we have the calculus, the Cartesian derivative, which can be retrieved from the parametric representations here. And so I thought this was just a nice example of using this. Again, you don't have to memorize this. There's no reason to do that. That's where I don't always agree with textbooks. If everything's memorized, then you can't check anything. You write the work down and it really doesn't matter if you look at it, if you evaluate up here or here, or evaluate here or here, they're equivalent. But since I circled these, I wanted to make sure I use those directly. But the thing is that understanding how things fit together allows you to make quick decisions. And unfortunately, math is not something that you learn in a small amount of time. It's over a long period of time. And so I want to emphasize for those of you that seem to find mathematics to be difficult, it's not something that is inherently difficult as long as you approach it. It's like I've taught many students since I've been at San Jac, and I would often tell my student that that was struggling, I'll say, you are very bright, but you're not a good student. What do I mean by that? I mean this: you must be responsible as a college student. That requires maturity, okay, and a focus on what you have to do. And that, my friends, ladies and gentlemen, is just a fact of reality, okay? I even convinced a student one time, they said, well, I'm not going to get a degree, Professor Ron, because I'm just, I'm smart and I'm just going to make my way. I said, wait a minute, you need the degree so you can get that great job, because you won't have any credentials. You can't walk up to a future employer and say, you need to hire me because I'm smart. Well, ladies and gentlemen, there are lots of smart people out there. Okay, there are lots of smart individuals. You have to set yourself up for success. So what I would say is always make an effort to be a better student. When students, I don't have this issue with you all. You all are good students, but the main thing is that be responsible as you work through your classes. Once you get to the university, that responsibility will take you to the next level, because every student in the class with you will be likewise bright, will be likewise intelligent. Think about it, ladies and gentlemen. They've been taking the same classes. They've been working hard to hone their skills and to become excellent. Okay. So what's going to separate you from the other students? Your work ethic, your responsibility. So as you work for the final, as you prepare for the final, remember we've got 2 times 10, 20 questions. And I gave you a list of the things. I think you'll find that the exam will be very fair and very straightforward. Get your homework done. It's due 11 p.m. this Wednesday. Okay, no more extensions. But I want to thank you all for being very good about getting your homework done. You've worked hard. I appreciate that. Just remember that your final exam will rest between Thursday and Friday. Pick a good time. Hopefully by now, all of your other teachers have already barraged you with their final exam, and Professor Ron is going to give you more time because he's a good guy. And I know that I have required a lot of you, but I know where you want to go, and I want you to be prepared for that. So thank you for your attendance today. Get some rest if you need it. Okay, get some sleep. Bring the stress down. And you're thinking, oh, Professor Ron, I have a million things to do. How am I going to get any sleep? But if you need to take a 30-minute nap just to bring the stress down, do it. I'll send out the invitations for the conference hours if you need some additional help, or certainly send a message via WebAssign, and I'll be glad to get back with you. So it's almost over. So congratulations to everybody. I'll say 50% congratulations. And then of course, when you're finished with your final, you can prop your feet up and rest. So everybody have a good day. Let me know if I can be of assistance, and take care of yourselves. We'll see you soon.